Dear Professor Deligne, first of all, we would like to congratulate you warmly as the 11th recipient of the Abel Prize.
Thank you.
Apart from that, this is a very big honor of being selected among many candidates. The Abel Prize also carries with it a cash amount of, I believe it's 6 million Norwegian crown, a little bit more than $1 million US. And we are really curious to hear what you plan to do with this money.
Yes. I feel that in a way this money is not really mine, but belongs to mathematics, and that I have the responsibility of trying to use it wisely and not in a wasteful way. So what I had in mind, but details are not clear yet, is about a tenth of it each for the two institutions which have been so important for me, the IHES in Paris and the Institute for Advanced Study in Princeton. And then also I would like to give money to support mathematics in Russia. And then the two institutions I have thought about, one is the Higher School of Economics, or rather the Department of Mathematics of the Higher School of Economics, which I think is now one of the best places in Moscow. It's much smaller than the McMath at the university, but very good people are there, and the student body is maybe only 50 a year, but I think also it's some of the best students. And it has been created by economists, I think, who try to do really the best, and this department is kind of giving prestige to the whole Higher School of Economics, and they've been very good with the department. So I think there some money could be well used. And the other institution which I would like to give some money, not that the money is important to them, but for me it's more a way of expressing my admiration for the work they do, is the Dynasty Foundation, founded by Russian philanthropist Laymen. And one of the, I think, very few foundations in Russia who give money for science, and in addition do it in a very good way. There are money for mathematicians, for physicists, for biologists, especially for young people, and this is really crucial now for Russia, and also vulgarization for a more general public, publishing books, vulgarization book. And so I think that this work they do is, I want to express my admiration for them in some tangible way.
The Abel Prize is certainly not the first important prize in mathematics that you have won. Let me just mention, first of all, the Fieldsmantel that you earned 35 years ago, I believe, the Swedish Crawford Prize, the Italian Balzan Prize, and the Israeli Wolf Prize. So how important is it for you as a mathematician to win such prestigious prizes? And how important is it for the mathematical community that such prizes exist?
For me, personally, it's nice to be told that mathematicians I respect find the work I have done interesting. Maybe, especially for the Fields Medal, it helped me to be invited to the Institute for Advanced Study, for instance, so it gives some opportunity. But otherwise, I don't think it changed my life much. For the general public, I think it can be very useful. It's kind of a pretext for speaking about mathematics and explaining to a general public what it is about. And one thing I find especially nice about this Abel Prize is that it's not just giving a prize to someone, but they are all connected activities directed to young children, some competition, and also, for instance, is the Abel Prize for the very good high school teacher. And as my experience shows, a very good high school teacher can be very important for the development of mathematics in somebody who is interested. So I think all of those activities are marvelous.
Okay, after talking about these prizes, we'll start with your early mathematical experiences. You were born at the end of the Second World War in the vicinity of Brussels, and we are curious to hear about your first mathematical experiences. In what respect were they fostered by your family relations, by school, and can you remember some of your first mathematical experiences?
A few things I remember. I am lucky that my brother is 7 years older than me, so when I looked at the thermometer and see positive and negative number for temperature, he could try to explain to me that -1 times -1 is +1, which was a big surprise. Then later, when he was in high school, he could tell me of the second degree equation, and he was at the university, he could give me some notes about the third degree equation, and the idea that one has some formula for third degree equation I found very interesting. But then I had really a stroke of extraordinary good luck. I was in the Boy Scout, and I had a friend there whose father was a high school teacher, and so I met the father. I spoke a little about mathematics, I guess, and he found that I was interesting, that he would help me, and he helped me in a number of ways, a very important one being to give me my first real mathematic books, the set theory of Bourbaki, which is not an obvious choice to give to a young boy. I was 14, I think. And so I spent at least 1 year, I think, to digest all of that. I guess I had some auto lecture on the side also, but and I think one nice thing of learning math at one arm's rhythm like that is that come extraordinary surprises. Like I had some idea from integers or to go to rational number, real number, but really it's in Bourbaki that I remember looking a little ahead of the page to see how one could define integers just from set theory, and this was a big surprise. And I had other big surprise like this. I don't remember whom gave me, a friend of the family gave me a book on complex variables, and then to see that the story of complex variable is so different from the story of real variable, that one's differentiable, it's analytic, power series expansion. So all those things which usually one use maybe somewhat bored at school, for me it was each time a tremendous discovery that such things were true. And then Monsieur Ness, this high school teacher, put me in contact with Jacques Tits, and that's how I could follow some, when I was still in high school, I could follow some course of Tits in University of Brussels and some seminar, and then that started being real mathematics.
It's quite amazing to hear that you studied Bourbaki, which is, I mean, usually is considered quite difficult already at that age, and complex analytic function theory is something that you usually meet at a, I mean, much more advanced level. Maybe you could also tell us a little bit about your formal school education. Was that interesting for you at all, or were you sometimes bored then when you?
I think what I like, I have a very good elementary school teacher, and I think that I learned much more in elementary school than I learned in high school, like how to read, how to write, arithmetic, and he was really enthusiastic for many things. There is one experiment he did about mathematics which I remember, which made me think about what was the proof. what is a surface, what is a length. It was not the reason for the experiment, but it was a half sphere, and to compare the surface of a half sphere with surface of a circle, and it was putting a rope around it to cover the whole surface and comparing it with what's happening on the for a circle. And this made me think a lot. Also, when I was in high school, I liked very much the problem of geometry. There are many nice things about it. There is a problem in geometry. Making a proof makes sense. One proves something which is not obvious, but it's not too difficult. And one can think for a few hours or a few days, why are those 3 points beyond the same line? But there also at the very beginning, I saw that was not really proofs. Those things of the axioms were really shaky. That I understood also. But once the axioms were passed and it was proving non-obvious things, that was very pleasant. And I feel that this might be lost now if one does not do geometry in high school, because I think it's the only place in mathematics where proofs make sense at that level, when it is not too difficult and not too easy, and when one has surprises on the way. And also, I think it was an excellent exercise to write proof, because then it's not only math, but it's, in my case, French also. One has to write in correct French to argue why this is true. And this connection between language and math exists there in geometry. If it is algebra, you write a sequence of equations, the logic is not apparent, and the power of language is not apparent also.
I just want to inject one thing. You went to the lecture of Jacques Tits at university when you were 16 or something, and there is a story that 1 week you were away on a school trip. And
oh yes, and Tits, I was told this story much later, that Tits came to give the lecture. He asked, but where is the link? And it was explained to him I was on a school trip, and then the lecture was postponed for the next week.
So he must already have recognized you as a brilliant student. So maybe we should just tell that Jacques Tits, he's also a recipient of the Abel Prize that was 5 years ago, together with John Griggs Thompson for his great discoveries in, all sorts of group theory, I would say. So he was certainly your most influential teacher. At the early time,
yes. Oh, and one nice story I have about Tits also, that sometimes to teach, the most important thing is what you don't do. He wanted to prove that the center of a group is an invariant subgroup. And he started giving the proof, and then he stopped short and telling, but I've been able to define the center, so it's fixed by any symmetry of the data, so it's made it obvious that it is invariant. And for me, this was a revelation, the power of ideas of symmetry. So the fact that it did not give a step-by-step proof, but told that symmetry make it obvious, this has influenced me a lot. I have kept a very big respect for symmetry, and in about any of my papers, there is somewhere an argument by symmetry consideration like that.
Going back to this early experience somehow, yeah, okay. Can you remember in which way Tits discovered you as a mathematical talent?
That I really cannot tell. I think it's Monsieur Ness who told me I was taken care of, and he did take very good care of me. There was at that time his course, then there were 3 really active mathematicians in Brussels, Tits, Bingen and Walbrook, organizing a seminar with a different subject each year, so I attended that seminar. And I learned very different topics like that. There was 1 year on Banach algebras, which was Walbrook's specialty, 1 year on algebraic geometry. And then, I guess the 3 of them decided it was time for me to go to Paris, and they introduced me to Grothendieck, told me I would go to Grothendieck seminar, attend Serre's lectures, and this was excellent advice.
Excellent advice, which can be a bit surprising for an outsider. One would like to think that Tits, I mean, being interested in you as a mathematician would somehow try to capture you for your own subjects in group theory and buildings and so on. But it didn't do that.
It didn't do, no. I felt that he looked what was best for me and act accordingly.
Yeah. Before we proceed to go into your future career, your further career in Paris, maybe we should try to give some explanations of what your subject somehow is about in very broad terms. And your subject in very broad terms is algebra, or algebraic geometry with all its connections to other subjects. I remember when Fields medalist Tim Gowers had to explain your subjects to an audience when the Abel Prize was announced earlier this year. He began by saying that that was a really difficult job for him to do, because on the one hand it was difficult to show some pictures that gave the right flavor. It wasn't so easy to find some easy applications for the subject either. So, but would you nevertheless try to give the big audience here a flavor of what the subject is about, some problems, some specific things where algebra and geometry are connected to each other, please?
So, the word tells part of the story, algebraic geometry, and that's always very nice in mathematics where two different frames of mind came together, and this gives a lot of intuition. So I think there is a saying of Descartes that geometry is the art of making correct reasoning on false figures, and I think figures has to be plural, and so it's very important to have various perspectives on question and know in way in which each perspective is false. So algebraic geometry, one has both the intuition from algebra, manipulating equation, and geometry when one can draw pictures. And in a way, it's a subject to whom many people have been exposed when one makes graphics, or one knows that an equation of the first degree is a way of describing a line in the plane. That something like x squared plus y squared equals 1 is a description of the circle. But if you have on the one hand the picture of a circle and on the other hand x squared plus y squared equals 1, it evokes completely different images in your mind, and you can try to play one against the other. For instance, a circle, that's a wheel, and a wheel turns, and so it's interesting to see what is the analog in algebra of this property of a wheel turning, and this will mean that you can make some algebraic transformation of x and y which map the circle to itself. And it's a second degree equation, so this tells you about intersection of a line, that there will be two intersection points, which you see also geometrically, a circle and a line, you have sometimes two intersection points, never three. But the algebra will give some additional properties that, for instance, if the line has rational equation and one of the points has rational coordinate, the second will also have. And so you have the geometric picture, the algebra, and this can also have arithmetical application if you restrict coordinate to be rational number, for instance, ordinary fractions, and also the fact that you have expression, algebraic expression, polynomial, you can use the same expression in number system which are not usual. There are some finite set on which you can define addition and multiplication, and you can look at equation in those finite sets, and this looks somewhat combinatorial. You try to count number of solutions in some finite set of solutions. But you can continue to draw the usual picture. You just know in a new way in which the picture is false, and you can use this geometric intuition to look at combinatorial problem. And in a way, I was never really central in algebraic geometry. It's all the things touching to it which I have been most interested. And in a way, algebraic geometry touch many subjects, because as soon as polynomial appear, one can try to think about it geometrically. Like physicist means Feynman integral, where you have an integral with polynomial expression or radical of them appearing, and so algebraic geometry can tell something about it. One can look at equation in rational number, in integers solution, and there also, it's not obvious at all, but algebraic geometry can contribute to understand what is happening. Or there is the very old story of elliptic functions, which are used for many even practical purpose, and there also you have integral of 1 over some square root of algebraic expression, and to understand how those integrals behave, the geometric interpretation is really crucial. So that's about the, so it does tell nothing about my work, but it tells about the subject and how there are all those connections which help to understand what is happening.
You came to Paris on the advice of Jacques Tits, and of course there you met two very central mathematicians, namely Alexander Grothendieck at IHES at Bure, and then Serre in Paris. Could you just tell what was your first impression of meeting or hearing these two mathematicians?
Yes, Grothendieck Tits introduced to me during a Bourbaki seminar, and I was really taken aback. He has this shaved head, very tall, very kind, but he did not know whom I was at all. I was nothing. Then I went to his seminar later, and I was still very ignorant, and in his lecture he was using all the time the word cohomology object. And in fact I knew what he was. I did not know the vocabulary, but and so at the end of the lecture asking, but could you tell me what do you mean by cohomology object? And I think that was really typical of him. Other people could have thought that if I did not know what this was, then really it was not worth speaking with me. That was not his reaction at all. Very patiently it tells me that if one has a long exact sequence, one takes the kernel of a map, one divides by the image of the previous one, and that's what it is. I knew it is for abelian group, and here it was in an abelian category. But I think he was extremely kind. One could ask apparently completely stupid questions. So being with him, I have no, I was not shy at all of asking questions which could be completely stupid. And I've kept this habit until now. I usually sit in front of the audience attending a lecture, and if I have something I don't understand, I ask, even if I would be supposed to know what the answer is. Then I was very lucky that he asked me to write up some talk he had given the previous year. He gave me his notes, and really I learned many things, both the content of the notes and also a way of writing mathematics, both in a very prosaic way, that one should write only on one side of the paper and leave some blank space so that he can make comments, but also one thing he insisted is that one is not allowed to make a false statement. And that's extremely hard. Usually one makes some shortcut, one knows this is true up to sign or something like that. This would not pass muster with him. Things have to be exactly correct and precise. So my first version of this reduction was, he told me, much too short, not enough details, it has to be completely redone, and that was very good for me.
What about Serre?
Serre is a completely different personality. Grothendieck liked to have things in their natural generality, to have an understanding of the whole story. Serre lacks, he has everything, Serre, but he lacks more flowers and beautiful objects. He was giving a course on elliptic curves where many different things come together. Then something about automorphic forms also. So it's very different. Serre has a much wider mathematical culture than Grothendieck has. Grothendieck redid everything for himself in case of need. And Serre could tell people to look at this. I think Grothendieck knew from the algebraic geometry of the Italians, basically through Serre and through Dieudonné, because he did not read essentially anything. He was writing only, not reading.
But I think I heard you said that you needed to go to Serre's lecture to keep your feet
on the ground. Yes, because there was a danger of Grothendieck of being swept away in generalities which wouldn't. Grothendieck never did generalities, in my opinion, which proved fruitless. But it's quite easy to be swept away by generalities which nobody will need afterward. And so Serre was a good, and he told me to look at different things, which all proved to be very important for me.
It's your perhaps most famous result, well, it is the most famous result, is the proof of the so-called Weil conjecture, the hard Weil conjecture, number 3 I think it was in the list. Before we get into that, could you try to explain why was the Weil conjecture so important?
There were some theorems of Weil before about curves, so a one-dimensional situation, and curves in some way, there's many analogies between an algebraic curve over a finite field and a rational number. And for the rational number, a central question in mathematics is the Riemann hypothesis, and Weil has worked out some analog of the Riemann hypothesis for curves over finite field, and that was proved. And he looked at higher dimensional situation too, and it was at the time when one was beginning to understand the cohomology of simple algebraic varieties like Grassmannian, and he saw that some point counting for objects over finite field were reflecting what was happening over the complex number and the shape of the similar space over the complex number. And so this was one of there were two stories in those Weil conjecture. One was, why should there be a relation between apparently combinatorial question and geometric question over the complex number, and what was the analog in those situations of the Riemann hypothesis. So that was the story from the point of view of Weil, I think. And then when there were two kinds of applications which came out, the first already done somewhat by Weil, that this was implying some estimate for some arithmetical function. For me, that's not the main import of the Weil conjecture. For me, the main import first is what Grothendieck did to construct the formalism which explain why there should be a relation between the story about the complex number when one has shape of spaces and the kind of combinatorial story. And the other is that this gives some symmetry properties for algebraic varieties over finite fields. One has some endomorphism, and it makes the whole situation very rigid. And then one can transpose back those information to the in the world of we are used to of working over the complex numbers. And so this gives very important constraint on what happens in classical algebraic geometry. And I think this is what has had the most important application then to representation theory and such things. It was not obvious at first, it would be the main application, but for me that's the most important part of why this is an important concept.
Grothendieck, of course, had a program how to prove the Weil conjectures, and of course it didn't work out that way. That your proof is different. And could you comment on what Grothendieck's program, did he have some influence on the way you finally proved it?
No, I think in fact the program of Grothendieck has been an hindrance to finding the proof, because with his influence people were just thinking in that direction on how to find the proof. In a way, if one could have followed this program, it would have been much more interesting. It would have explained a number of other things which one wants to explain. But all this program relied on finding enough algebraic circle on algebraic varieties, and on this question one has made essentially no progress since the 70s. So here I used a completely different idea inspired by work of Rankin for automorphic form, himself relying on work of Landau about properties of L functions, and this did the trick. It still has a number of applications, but it was not realizing the dreams of Grothendieck.
No, because we heard a report that Grothendieck was a little, well, he was glad that it was proved, of course, but he was a little disappointed.
Oh yes, for good reason, I would say. It would have been much nicer if his program could have been realized, and he was not thinking there would be another way to do it. So when he heard I had proved it, he felt sure I must have done this and that, which I had not done, and so that was the reason of the disappointment.
I see. Because, I mean, there has been some comment, metaphorically speaking, that between two peaks, Grothendieck would have filled in the valley.
Yes.
But while you build a suspension bridge.
Yes. And this is not as nice, but still it works.
Okay. But you have to tell us the reaction of Serre when he heard about the proof.
Ah, yes. So it was, I don't think I had a complete proof yet, but I had some crucial case, so it was clear things, at least big part of it was accessible. And so I wrote him a letter, and I think he got it just as he had to go to the hospital for some operation of this Achilles tendon which he had broken. So he got this letter and he was going in an euphorical state to the operation room because he knew now that this was roughly done.
Very good. What about beyond the vehicle? I mean, first of all, we should say that, I mean, the praise that we have read about your proof, I mean, from various people that know it's, this is such a marvel of a proof, using all these ideas, however you came about it. Can you describe something about how you got these various ideas?
In part, it was lucky that I had all the tools at my disposal at the same time, and that I understood that those tools would do it. For instance, and later on there have been some simplification of the proof by Laumont afterward, and a number of those tools are no more needed now. But at that time, Grothendieck had some idea about families of hyperplane section of an algebraic variety, and extending, putting in a purely algebraic framework works of Lefschetz in the 30s. And in particular, there was a famous statement of Lefschetz later proved by Hodge, so-called hard Lefschetz theorem. And Lefschetz was very topological, and contrarily to what one thinks, if things are very topological, there is more chance to translate them in abstract algebraic geometry than the proof given by Hodge, which was very analytic. So Grothendieck asked me to look at this book of Lefschetz, which is beautiful, very intuitive book. And so that's one of the tools I had at my disposal. Then I was interested in a number of things, in particular automorphic form, and I think Serre told me that there was this estimate of Rankin, which is interesting. And so I looked carefully at Rankin estimate, and in fact, Rankin was getting some non-trivial estimate by rather sophisticated means, but the basic idea was that a sum of square is positive. And I could see that the same tool in a much less sophisticated way could be used here, because essentially of work of Grothendieck we have some L function and we were understanding the pole because of work of Grothendieck, and this was enough. The poles were much easier than the zeros, and it made it possible to use Rankin's idea to this question. So it happens that I had all of this at my disposal. One has to put it together, but that I cannot tell how it was done.
Yeah. Well, by the way, the Rankin thing, Atle Selberg independently discovered the same bound as Rankin did, but he came after Rankin. But that's just a comment. Yes. So what about the other results that you have proved after the Weil conjectures? Are there any that you would like to, you're particularly fond of, or?
Yes, one which I like very much because he used a lot of things happening in algebraic geometry. I did construct some structure on cohomology of algebraic variety, mixed odd structure. And here, even it does not appear in the final written version, ideas of Grothendieck above motif proved really crucial. One very surprising fact about algebraic varieties, one has those invariant attached to them, but very strangely, there is this invariant called cohomology, but it comes in a very large number of different aspects. And the philosophy of motif is that it should all be the same story told in different language, if I might say. And so, if one has something one can do in one cohomology theory, one should think that it has to be possible to do it in all cohomology theory. If one applies this principle to L-adic cohomology and apply it to Hodge theory, one obtained a theory of mixed odd structure. Of course, it requires some work, but the feeling that something has to be possible came from this philosophy that the same story is told in many languages, and that one has to understand what is common, and one has to be carried over from one setting to the other. And when one is convinced that something has to be true, often one can find the proof, but the main thing is to understand why it has to be true.
Yeah. By the way, a question about algebraic geometry, which is of course one of the main areas of mathematics. Would you say that at least for a beginner in mathematics, to learn algebraic geometry requires much more effort than other areas of mathematics?
I think to enter the subject is hard, yes, because one has to master a number of different tools. First, cohomology is indispensable to do anything. Then Grothendieck there's been a number of stages in algebraic geometry. There is the Italian school, which were a little hazy, and the theorem had as exceptions. Then Zariski and Weil somewhat put it in somewhat better footing, but difficult to use. And then there came Serre and Grothendieck, who gave a new language to express all of that. And this language is very easy, no, not easy to use, but it's very powerful. This language of schemes, one can do a lot of things. It covers both arithmetical application and more geometric aspects, but it requires some time to understand the power of this language. And then, of course, there are a number of basic theorems, but I don't think that's the main stumbling block. The more difficult is to understand the power of this language created by Grothendieck and how it relates to usual geometric intuition.
What about the Langlands program? Have you been engaged?
I've been very much interested in it, but I contribute very little, only for GL2, linear group in 2 variables did I work on it. I tried to understand things. So a somewhat removed application of the Weil conjecture has been Go recent proof of what they call the fundamental lemma, but I did not do a lot of work in it. I have a lot of interest in it.
Now, some questions about your way of working. First of all, at least when we look at your CV, we can see that apparently you have not taught big classes of students very much. So in a sense, you are one of the few full-time researchers in mathematics. Is that correct?
Yes, and I find it I am very lucky to have been in this position. I have never had to teach.
Well, some people like it to teach, but
I like very much to speak with people, and the 2 institutions where I have been, young people come, and then I can speak with them. I can sometimes answer questions they have. More often they ask a question and I can ask them a counter question, which can be sometimes interesting too. So this aspect of teaching, one-to-one contact and how to give useful information and learning in the process, I have it, and it is important. I expect that what must be very painful in teaching is having to teach to people who are not interested and who are forced to learn math because they needed to have some grade to do something else. That would have been repulsive for me.
In the beginning, you told us already about the 2 institutions you have mainly been affiliated to, the Institut des Hautes Études Scientifiques at Bure-sur-Vette, close to Paris, and now since 1984, I believe, the Institute of Advanced Study in Princeton. So it would be interesting for us to hear what were your motives for leaving the IHES and moving to Princeton, and also how in retrospect you would somehow see both what unites the 2 institutions and also how they are different.
So I think the reason I left, there are 2 of them. One is that I was feeling it was not good to spend all one's life in the same place, that some variety is important. One thing which did not work is that I was hoping to have contact with Harish-Chandra, who has done such beautiful work in the theory of representation and automorphic form, because that's part of the Langlands program in a way in which I am very interested, but unfortunately Harish-Chandra died not shortly before I arrived in Princeton. And another reason is that I had imposed on myself to give a seminar each year on a new subject in Bure, and it was a little too much. I was not really able both to give the seminar and to write things down, and I did not impose myself the same obligation when I went to Princeton. So that's a reason for the move. then in Princeton, it's bigger also in the fact that there is not only math and physics, but also history and social sciences. But this is some pleasure of speaking and learning things about which one knows nothing, but scientifically there is no real interaction, I would say. It's just pleasant to be able to hear a lecture about ancient China, but just cultural interest, I would say. With physicists, it's scientifically interesting.
Apart from your excellent connection with French mathematics at first and US mathematics now, you have also for a long time had very close contact to Russian mathematics, even before the fall of the Iron Curtain. So how did your contacts to Russian mathematics develop?
First, it was just, I think Grothendieck told Manin, who was in Moscow at the time, or Serre told him that I had some interesting work, and they invited me to a conference. The academy invited me because of them to a conference for Vinogradov, this terrible anti-Semitic person. And I went, and I was really, I find it a beautiful culture for mathematics. At that time, mathematics was one of the few subjects which the Communist Party did not understand at all, so could do nothing about it. It was a space of freedom. And it was very visible, and so one would go to somebody's house, sit at a kitchen table and discuss mathematics with a cup of tea. And I fell in love with this atmosphere and this enthusiasm for mathematics. And also it was excellent. It was one of the best places of the world at that time. Now there are still some good people, but there has been a terrible immigration of mathematicians, because just to earn their living, they had to go abroad at least half of the time. So that was my introduction to Russian mathematics, and I have some nostalgia for those beautiful memories of being in Moscow, speaking with Manin, with Bernstein, being at Gelfand seminar. And there is a lot of tradition which I find worthwhile and which have not died. Like there is a very strong connection between university and secondary education. People like Kolmogorov had big interest in secondary education, not always for the best. It was maybe a little too new at the time, but also they have a system of Olympiads. I think they are very good of detecting early promising people in mathematics and being able to help them. There is this culture of seminar which is in danger, because it's important that the head of the seminar be full-time in Moscow, and now it's not always the case. So there is a whole culture which I think one should try to preserve. And so that's why I use half of the Balzan Prize to try to help young mathematicians, because
contest that you inaugurated, yes. Right?
Because the system at the top is kind of falling apart because there is no money to keep people, but the infrastructure was so good that the system continued to produce very good young mathematicians. And so one has to try to help them, and if possible, make it possible for them to stay somewhat longer in Russia, so that all those traditions can continue.
Different type of question. Some scientists, also some mathematicians, are very much driven by the aim of being the first to make a major discovery. This seems clearly not to be your major driving force.
I don't care at all, no.
So, I mean, what about this culture in general? Could you come with some comments?
I think for Grothendieck it was very clear. He once told me that mathematics is not a competition sport. Of course, there are many different kinds of mathematicians, and some will want to be the first, maybe more if it is solving a very specific, difficult question. But otherwise, for me it's more important to have the general picture, to create tools. For me it's much more a collective enterprise, and also collective enterprise of long duration. In contrast to what happens in physics, in biology, articles have a very long, useful life. So, for instance, there are all now those automatic evaluation of people using various criteria, and for mathematics it's particularly perverse because some of those evaluations take account only of papers published in the last 5 or 3 years, and this makes it completely meaningless for mathematics. I think when I have a bibliography, at least half of the paper can be 20, 30 years old, and some will be 200 years old also.
So maybe some words about your work style, your particular work style in mathematics. When you begin to work in a new mathematical area, are you most often guided by examples, by specific problems, by computations perhaps, or are you rather, I think you said it already, are you rather surveying the landscape, looking for connections?
For me it's this. First I need to get some general picture of what should be true and what should be accessible, what tools can be used. So for one sign of this, when I read papers and try to remember, usually I will not remember details of the proof at all, but I will remember which tools were used. And another thing, it's important to be able to guess what is true, what is false, not to do completely useless work. And then I don't remember statements which are proof. I try to have a collection of pictures in my mind, and more than one picture, all false, but in different ways, and I know in which way they are false. And then for a number of subjects, if the picture tells me this would be true, I take it for granted and I will come back to the question.
Can you elaborate a little bit of what kind of pictures you have of these very, very abstract?
Sometimes very simple things, like I have to think I have some algebraic variety, I look at hyperplane section and I want to understand how the two are related. I look at the pencil of hyperplane section, and so here the pictures are very simple. I draw just in my mind something like a circle in the plane and a moving line which sweeps it, but then I know that this is false, that it's not one-dimensional but higher dimensional, that it's not two intersection points coming together, but a more complicated picture where like a conic which becomes a quadratic cone. So, but it's always very simple picture put together. Or I know that I have a map from something to another. I see a number of properties it has, and I am quite sure then that it's just a most simple kind of map, a smooth map, if some properties are satisfied. Yes, I was a little wrong in what I was telling. It's just not I have a collection of pictures, but I have also a collection of simple counterexamples. And some statement I can hope to be true has to be checked against both.
So you are thinking more geometrically than algebraically? Yes. Yeah.
Some people say that in mathematics, good conjectures or even good dreams are at least as important as good theorems. Would you agree?
Really, because the Weil Conjecture has created a lot of work, and because the question was still very vague, but that's all right. But that there should exist some cohomology theory for algebraic with some properties, this has made 20 years of work or a little more to really get through it. Another example of dream is this Langlands program that has been 50 years of work now by many people to get a little better grasp on what is happening. And there is this philosophy of motifs of Grothendieck where very little is proved. A number of variants of it exist which take some of the ingredients. Sometimes it can be used to make actual proofs, but often it can be used to guess what should happen and to try to prove it in another way. So those are examples of dream or conjecture which are much more important than specific theorems.
And to follow up that, you also like to write letters to other
yes.
mathematicians.
I find writing a paper take a lot of time, and it's very useful to have everything put together and correct, and one learns a lot, but it's also somewhat painful. So at the beginning, when one is forming his ideas, I find it very convenient to write a letter. Often it's a letter really to myself, but I send it to somebody else. It helps because I know that this person, I can assume this and this and this, which I have not to dwell about, and so some shortcut will be all right. And then sometimes this letter will stay in a drawer, a copy of it for a few years, but then many ideas are in it, and when I have to write the paper, this is a blueprint for what will...
But when you write a letter to another person, which so comes up with some other ideas to, you know, develop your own idea, that results in a joint paper that...
that can happen, yes.
Yeah.
Mm-hmm. Yes, I have collaborated, and quite a number of my papers are me alone. Some are people having the same ideas, and it's better to make a joint paper than to wonder what is what. There are a few cases of genuine contribution where different people bring different intuition. This was the case with Lustig, for instance. Lustig had the whole picture of using L-adic cohomology for group representation, but he did not know the technique at all. I knew the technical aspect of L-adic cohomology, and I could give him the tool he needed. So that was real collaboration in that sense. There is the joint paper with Morgan, Griffiths, Sullivan, and there it was also genuine collaboration. Or also the one with Bernstein, Bellinson, and Gaber. There also we had different understanding and putting them together.
Do you have had any, what I call a Poincare moment, that in a flash you sort of see a solution that you maybe have worked and thought about for a long time?
I don't. The closest to it maybe was the Weil Conjecture, where I understood that there maybe was a path using ranking against Grothendieck, against the location of the pole by Grothendieck, but it took a few weeks after that to be able to really it worked. Otherwise, it's more a slow development. And maybe the definition of mixed structure, I computed a completely trivial example, and no, it would always, here also it was progressive. Some example give me hope, and then I can do it. But a complete solution in a flash, surely not.
When you look back through 50 odd years of doing mathematics, isn't that right? How have your work and your work style changed over the years? Do you work as perseverant as you did it in your young years, or is mathematics rather a young man's game, as Hardy put it once?
I think Hardy is right. In French I would say that I have still que fait des beaux restes. But so I'm not as strong in the sense I cannot work as long as intensively, I don't think I have as much imagination, but I have much more technique. So this counterbalance to some extent, and also because I have this technique and contact with many people, this helps a lot. They give me some of the imagination I am lacking, and I bring the technique, and then the work can be useful. But I'm not the same as I was when I was 30, no.
You've even retired from your professorship from the...
Yes, but that's a purely formal story. It means retirement money instead of salary, and no meeting of the school for selecting the member of the next year. So that's all for the best. It was even more time for doing mathematics.
Yeah, that was my impression. Another very general question, when you look at development of algebraic geometry, number theory, I mean the fields that are close to your heart, are there any problems, any areas where you would like to see progress soon, some problems maybe that may be solved, or is there anything that you give most significance?
Significance I can tell. Whether it is within reach in 10 years or not, I have absolutely no idea. And I think that's the way it should be. I must say, even for some previous problem, like when Faltings proved a model conjecture, in my mind it was completely inaccessible, and I proved wrong. So if I was doing any kind of prediction, it was... I think for me, what I would much like to see progress on is better understanding of the story of motifs. But which path to take, what is the correct question, that's very much in the air. Grothendieck program was relying on proving existence of algebraic circle with some property. This to me looks hopeless. I may be wrong. I think it's not the only way, and there are a few questions I can think which could be a substitute, at least in some cases, for that. The other kind of question I would like very much to see progress is this Langlands program, but that's a very long story. And then, yes, I think a third domain where I would like to have understanding is that the physicists come with conjectures which for me are completely unexpected, using completely illegal tools. But so far, whenever they've made a prediction, like numerical prediction how many curves of some kind of some surface, and it's big numbers in the million perhaps, sometimes there's been previous computation by mathematicians. It was disagreeing with what the physicists were predicting, and the physicists were right. So they've put their answer something really interesting, and we are completely unable to capture their intuition so far. Sometimes they make a prediction and we made a very clumsy proof of it without really understanding. That's not how it should be. And in fact, it's somewhat worse. For me, one of the aims of this program we had with the physicists, I wanted not to have to rely on Witten and be able to make conjecture myself using those tools. And I failed. I did not understand enough of their picture to be able to do that. So I still have to rely to Witten to tell me what would be interesting.
What about the Hodge conjecture?
For me, this is part of the story of motive. And whether it's true or false for me is not a crucial story. If it is true, that's very good, and it kind of solves large part of the problem of constructing motif in a reasonable way. But if one can find some notion of circle which is not really algebraic, and there are a number of candidates which fulfill the same purpose, I am as happy as if the Hodge conjecture was solved. So for me it's really motif, not Hodge, which is crucial.
We have the habit of ending these interviews by asking questions that are outside of mathematics, just for a moment. So could you please tell us a little bit about your private interests outside of the profession? We know a little bit about your interest for nature, gardening, for example. Maybe there are others.
That's the main interest. I find nature such a beautiful, the earth such a beautiful place, and walking. I don't like just to go to look at a place. I find that if you want to really enjoy the view from a mountain, you have to climb to it by feet. And similarly, to see the nature, you have to walk. Or to do gardening. So, as in math, to take pleasure in nature, and nature is such a beautiful source of pleasure, one has to do some work also. But that's my main. Yes, also I like to bicycle, because that's a way also to look around things. When distances are a little bigger than what is convenient by feet, this is another way of enjoying nature.
But we heard that you also build igloos in the winter.
Oh yes, that's something. Unfortunately, there is not enough snow every year, but when there is enough snow, and snow is very tricky. When it falls, if it is too powdery, it's impossible to do anything, and when it becomes crusty and block of ice, and it's also impossible. So there is just maybe one day or a few hours when one has to be willing to make the work, packing the ice, putting the construction together, and then the igloo is done.
And then you sleep outside.
Then I sleep in the igloo, of course.
But you have to tell what happened when you were a little child.
Yes. I was in Belgium on the seaside for Christmas, I guess, and there was a big snow. And my brother and sister, so we are much older than I am, had the nice idea of making an igloo. And I was a little on the way. I was there, looking and knowing them. Then they decided I could be useful to one thing. If they take me by the feet and the hand, I could be used to pack the snow. And that way I was useful.
So that might be a good point to end the interview. So thank you very much for granting us this interview. And these thanks come also on behalf of the Norwegian, the Danish, and the European mathematical societies that we represent. Thank you very much.
Thank you.